These are nodes from sections 2.2 and 8.1, which is on direct variation and inverse variation. Direct variation, it was in chapter 2 because it is a linear function. It's just if we have y equals some constant times x, y equals k times x, k can't be 0, so y equals 4x would be direct variation. Y equals negative 3x, y equals pi times x. Any of those are direct variation. Notice a linear function where the y-intercept is not 0. Y equals 4x minus 3 is not direct variation. It's only if our y-intercept is 0. Notice what happens with direct variation. If I have y equals 4 times x, if I start with an x value of 2, if I plug that in, I clearly get 8. If I double the x value, I double it, now it's 4. If I plug in 4, I get 16. Notice the y value also doubles. If I multiply the x value by 10, if I plug in 40, I get 160. My y value multiplies by 10. If I divide the x value by 3, so it was 40, let's divide it by 3, and now it's, or not 3, 5, divide by 5, and now it's 8. If I plug in 8, I get 32. 160 divided by 5 does give me 32. So if I multiply or divide the one variable by something, the other variable multiplies or divides by the same thing with direct variation. That does not happen with other linear functions. If I have y equals 4x plus 2, and I plug in 2, I get 10. If I double my x, now I have 4. 16 plus 2 is 18. So notice this is times 2, but this one's not times 2. That only works for direct variation. Section 8.1 is on inverse variation. Inverse variation, instead of k times x, now we have k divided by x. Again, k is not 0. Notice the constant is on top and the variable x is on the bottom, 3 divided by x, to get inverse variation. If I have y equals x divided by 3, x divided by 3, that's the same thing as 1/3 x. This is direct variation, not inverse. So you have to be dividing by your variable. You're dividing by x for inverse variation. If I have y equals 24 divided by x, let's kind of take a look at the same thing we just did. If my x value is 2, my y value is 12. If I double my x, so now it's 4, this is times 2. If I plug in 4, I get 6. Notice I am dividing by 2. If I times 6, now I'm at 24. If I plug in 24, I get 1. I divide by 6. If I divide by 2 for the x, 12, I get 2. It's times 2 on this side. So if I multiply or divide one variable by something, the other variable does the opposite. So as one variable gets bigger, the other one gets smaller for inverse variation. So example 1 says, suppose that x and y vary inversely. As soon as we see that x and y vary inversely, I would write y equals k divided by x. If it said directly, I would write k times x. It tells me x is 3 when y is negative 5. So x is 3, plug in 3 for x, when y is negative 5. We should be able to solve for k. Multiply both sides by 3 gives me k equals negative 15. So write the function that models the inverse variation. That's right here. Y equals negative 15 divided by x. And find x when y is negative 1. Plug in negative 1 for your y and solve for your x. Example 2 gives us a couple different tables here. And then the question wants to know, for each of these tables, do we have direct variation, do we have inverse variation, or do we have neither one? So for these, I would recommend starting by checking to see, could it maybe be direct or could it maybe be inverse? As my x values are getting smaller. My y values are getting bigger. If my x's go one way, they're getting smaller, and my y values are going the other way, they're getting bigger. It cannot be direct variation. The only thing we could possibly have here is inverse variation. So let's assume we have inverse variation, y equals k divided by x. It still could be neither. What we want to do is, can I come up with an inverse equation that works for all of these? So take any one of the points, I'm just going to take the first one, plug it in for x and y, and solve for k. I get k equals 0.72. So if it's inverse variation based on the first point, my equation is y equals 0.72x, or divided by x, 0.72 divided by x. So we know it works for this point. Check the other points. If I plug in 0.6 for x, 0.72 divided by 0.6 does give me 1.2. 0.72 divided by 0.4 does give me 1.8. It works for all 3 points. Therefore, yes, we do have inverse variation, and the equation is y equals 0.72x. We're going to skip part B here. Let's jump down to part C. My x's are getting bigger. My y's are also getting bigger. So I might have direct variation. Let's assume we do have direct variation. Y equals k times x. Plug in your point for x and y. Divide both sides by 0.5 gives me k equals 3. Based on the first point, y equals 3x would represent direct variation. And then check it for the other points. 3 times 1.5 gives me 4.5. That's not 6. I can stop right there. That equation did not work. That is the only possible equation that would work for the first one. So this one is neither. We do also have something called joint variation. If it ever says that variables vary, if x, y, and z vary jointly, that means that it's direct with all of them. So this right here would be read as z varies jointly with x and y. So if it ever says jointly, that just means it's multiplication for all of them. Combined variation, sometimes we may have a variable that varies inversely with one variable but directly with another. That is called combined variation. Example 3 tells us that z varies directly with x and inversely with y. So when it says that z varies directly with x, so I've got k times x, and inversely with y, that means I'm dividing by y. Notice we're writing one model, one equation that relates x, y, and z. So we don't want to do k times, or z equals k times x, and then z equals k divided by y as a separate equation. Direct with x and also inversely with y. Plug in your values to get k. We know z is 15 when x is 6 and y is 2. 6 divided by 2 can be reduced to 3. Divide both sides by 3 gives me k is 5. Write the model that describes the variation. Z equals 5x over y. Find z when x is 4 and y is 9. Just plug them in. 5 times 4 divided by 9 does not reduce. Oops. Last problem here, and it's a story problem. It says the volume of gas varies directly as the temperature and inversely as the pressure. volume, I'm going to call volume V, varies directly as temperature, so K, that's some constant, times temperature, and inversely with pressure, divided by P. It tells us volume is 230 cubic centimeters. I'm plugging 230 in for volume. When the temperature is 300 Kelvin, 300 in for temperature. K, here's my constant, not Kelvin. And the pressure is 20 pounds per square centimeter. Solve for K. So we've got 230 times 20, 4,600, equals 300 K, divide by 300, gives me K equals 46 over 3. So the equation is V equals 46 over 3 T over P. If this is a multiple choice question and it's asking you to write an equation, a lot of times instead of writing the whole fraction as K up here in the numerator, this is the same thing as V equals 46T. You move the 3 down to the bottom. Basically, you're multiplying times 46 over 3. So we've got 3P in the denominator there. This one wants to know, what is the volume when the temperature is 270 Kelvin? And the pressure is 30 pounds per square centimeter. So just plug those in and we should be ready to go. 46 times 270 divided by 3 times 30 gives me a volume of 138. Make sure you use the units. Volume in this problem is measured in cubic centimeters. So that is sections 2.2 and 8.1. If you have questions on anything, please reach out.